Hi, welcome to R&AC Academy. My name is Ram Prasad. Let me give a small brief about me. I did my masters in R&AC and then I worked for 25 years with various organizations involving in product development and technology innovation functions. I had 5 patents filed on my name. Out of my passion, I transitioned into teaching. Presently, I am into coaching GATE and IES aspirants on R&AC subject. I also conduct workshop on R&AC systems, faculty development programs, etc. for the engineering colleges. Recently, I conducted webinars for the members of ISHRE and ASHRE. Based on the response I received for the lectures on refrigeration systems, I am presenting here with a series of lectures on psychrometry, again for the benefit of the students and the professionals. I believe these lectures will also add a great value to all of you. This is the first lecture in the series of lectures on psychrometry. In this lecture, we will be discussing the psychrometric properties, but let me start with a small or a high-level introduction about psychrometry. Psychrometry is a field of science that deals with the behavior of moisture. Well, what is moisture? Moisture is the binary mixture of dry air and water vapor. Well, what is dry air then? Air that contains no water vapor is called dry air. We all know that air contains oxygen, nitrogen, carbon dioxide, etc., etc. All those gases excepting water vapor is called dry air. And the moment we add water vapor to the dry air, it will become moisture. Let me give an interesting perspective about the air conditioning field. At the fundamentals level, certain important declarations were made by our predecessors in the air conditioning field, for which we all must be thankful to them. Let me start with the first one. In moisture, the content of dry air is maximum and the content of water vapor is very small or very, very less. Also, the content of dry air is more or less fixed or constant. On the other hand, the content of water vapor is not only small but also changes continuously. For this reason, the psychrometric properties are defined per kg of dry air, not per kg of moisture, not per kg of water vapor. Why? Because the mass of the dry air in the moisture is more or less constant and hence all the properties in psychrometry are defined per kg of dry air. What is the benefit for us from this? Only because of this declaration, we are able to plot the state of the moisture on the psychrometric chart. Then, with this discussion, is there any significance for us to consider the presence of water vapor in the moisture? The answer is yes. The content of water vapor present in the moisture plays a significant role as far as the human comfort is concerned, and hence it is a serious consideration in all air conditioning processes. Now, let us take up another declaration which simplified the engineering calculations in psychrometry. That is, between 0 degree centigrade and 50 degree centigrade, both dry air and water vapor behave like ideal gases. Hence, the moisture also behaves like an ideal gas within the temperature range. Therefore, it is declared that the moisture can be treated as an ideal gas within the operating temperature range of air conditioning applications or between 0 and 50 degrees centigrade. What is the benefit for us from this declaration? With that declaration, we are allowed to use or adopt ideal gas laws in psychrometric calculations. This is one of the phenomenal advantage we enjoy while doing the engineering calculations in psychrometry. Let us now summarize the ideal gas laws that are used in psychrometry. The first one is PV is equal to RT and PV is equal to MRT. First V is the specific volume, meter cube per kg. The second one is absolute volume expressed in meter cube. P is equal to PA plus PV. This comes from the Dalton's law of partial pressures, where P is the barometric pressure, PA and PV are the partial pressures of dry air and water vapor respectively. The next, M is equal to MA plus MV, where M is the mass of the moisture, MA and MV are the masses of dry air and water vapor in the moisture respectively. Next, H is equal to HA plus HV. It comes from Gibbs' law. Let us now take the discussion to the psychrometric properties. The first property, dry bulb temperature. What is dry bulb temperature? It is the actual temperature of the moisture. If we hold a thermometer with its bulb exposed to a current of moving air, then the temperature that is read from this thermometer is called the dry bulb temperature of the moisture. The next property is specific humidity, W. It is also known as moisture content or humidity ratio. It is defined as the ratio of mass of water vapor MV to the mass of dry air MA in a given volume of moisture and at a given temperature. It is expressed as W is equal to MV divided by MA, and the unit for W is kg of water vapor per kg of dry air. As discussed in the previous slide, the mass of water vapor in the moisture will be very, very small. Hence, the more convenient unit for W would be grams of water vapor per kg of dry air. The formula for computing W would be 0.622 PV divided by P minus PV expressed in kg of water vapor per kg of dry air. And if we want the W expressed in grams of water vapor per kg of dry air, then the formula would be 622 PV divided by P minus PV. In both cases, the PV is the partial pressure of water vapor in the moisture and P is the barometric pressure. So looking at this formula, we can say that W depends only on PV. The next property is the specific volume of moisture. It is defined as the volume occupied by 1 kg of dry air. Please note here that the name of the property is the specific volume of moisture and the definition is the volume occupied by 1 kg of dry air. This is what I mean by the psychrometric properties are defined per kg of dry air. The unit for the specific volume of moisture is meter cube per kg of dry air. The actual volume of 1 kg moisture would be different from this, but the difference would be so small that it was decided to ignore the same. The next property is the density of the moisture, which is the reciprocal of specific volume of moisture, and its unit is kg of dry air per meter cube. The next property, dew point temperature. It is the temperature at which the first dew is formed when the moisture is cooled at constant pressure. Let me explain where we will experience the dew formation in our daily routine. Whenever we take out a cool drink bottle from the cooler, we will see sweat formation on the surface of the bottle. That sweat is nothing but the condensation of the water vapor in the ambient air. Why does it happen? Because the bottle surface temperature is lower than the dew point temperature of the ambient air. Next question is, how do we find the dew point temperature? Take a metallic tumbler with some water in it. Add small pieces of ice while stirring continuously. Keep measuring the temperature of the water, and the temperature at which we find the first dew formation on the outer surface of the tumbler is the dew point of the ambient air. The next property is enthalpy of moisture, and its unit is kilojoule per kg of dry air. The expression to compute the enthalpy is equal to Cpa plus W into Cpv whole multiplied by T plus 2500 W. Here, Cpa is the specific heat of dry air, Cpv is the specific heat of the water vapor, while T is the dry bulb temperature of the moisture. The expression in the parenthesis is also known as the humid specific heat of the moisture, Cp. In psychrometry, the Cp value had been approximated as 1.0216 kilojoules per kg dry air Kelvin. Therefore, the enthalpy can be expressed in a simplified form like this. However, there is an important note point here. In the context of academics, meaning for academic exams or for competitive exams like GATE, IES, etc., if the problem statement has the values for Cpa and Cpv, then you must use those values while computing the humid specific heat of the moisture Cp. Accepting this in all contexts, both academic and professional, we can use Cp is equal to 1.0216 while computing the enthalpy value. The next property is relative humidity. It is defined as the ratio of mass of water vapor in the moisture to the mass of water vapor in the air when it is saturated at the same temperature and volume. So, RH can be expressed as mV divided by mvs. mv is the mass of water vapor in the moisture and mvs is the mass of water vapor in the air which is saturated at the same temperature and volume. This can also be expressed as the ratio of PV divided by PVS. For dry air, the mass of water vapor is equal to 0 and hence the relative humidity for dry air would be 0. For saturated air, mass of water vapor and MVS both will be equal and hence the relative humidity for saturated air will be 100%. The next property is wet bulb temperature WBT. It is the temperature measured by a thermometer with its bulb covered by a wet wick and exposed to a current of moving air. The device that is used to measure WBT is called psychrometer. Psychrometer consists of two thermometers, out of which only one thermometer will have its bulb covered by a wet wick. When the psychrometer is rotated, the thermometer whose bulb is not covered by a wet wick gives us the dry bulb temperature of the moisture, and the thermometer whose bulb is covered with wet wick gives us the wet bulb temperature of the moisture. For saturated air, the dBT, WBT and dew point temperature, all three will be equal. There is one very interesting note point about WBT, that is, WBT is not a thermodynamic property of moisture. A parameter which is not a property of the system cannot be plotted on any coordinate system. But then, how come the WBT is appearing on the psychrometric chart? A valid and logical question. I will explain the answer to this question after discussing the next property of the moisture, that is adiabatic saturation temperature or thermodynamic wet bulb temperature. It is defined as the temperature at which unsaturated moisture becomes adiabatically saturated by the evaporation of water into it. The adiabatic process in psychrometry happens at constant enthalpy. Therefore, as per this definition, we must saturate the moisture by evaporating water into it while keeping the enthalpy of the moisture unchanged. The temperature of this saturated moisture is called adiabatic saturation temperature or thermodynamic wet bulb temperature. It is a thermodynamic property of the moisture, but it needs an elaborate setup to find the adiabatic saturation temperature of the moisture, and it cannot be carried along to the field. But fortunately for the air conditioning engineers, the adiabatic saturation temperature and the wet bulb temperature are very close for moisture. They are close by about 95%. The difference between these two values would be in decimal numbers. Hence, it had been declared that these two temperatures can be considered as equal in psychrometry. This is the reason why we are having WBT appearing in the psychrometric chart. These days we got good sensors to give accurate measurement of humidity. But during earlier days, people could plot the state of the moisture on the psychrometric chart by measuring the dBT and WBT of moisture using the psychrometer. With this lecture is completed. In case you have any questions, doubts, clarifications, etc., please feel free to write to me. The next lecture will be on psychrometric charts and psychrometric processes. See you then. Thank you very much.